Hello and welcome back to our series on electrical and computer engineering. Our conversation tonight is about two very powerful techniques of analysis: voltage dividers and current dividers. How many times when you have seen or have been part of a team of tug-of-war, you've wondered how much of the total effort was being put by each one of the members of the team? Well, electrical engineers ask themselves these questions whenever we see several resistors in series and a total voltage applied to the totem. We wonder, of that voltage, how many of those volts drop in each one of the resistors in series? That is a voltage divider. And also analogously, when we see a bunch of resistors in parallel and we pour a current to that group of parallel resistors, how much of the total current will flow through each one of the different resistors in parallel? That is a current divider. Let's see how this works, Let's begin.
We commence with a review of Ohm's law. In a resistor, if we know the current and the resistance, we can compute the voltage like that. Ri is the voltage in the resistor. But if what we know is the voltage and the current, we can compute the value of the resistor's resistance. R is V over I. And finally, if we know the voltage and the resistance, we can determine the current as V over R. That expression can be written also this way if we only remember that G, the conductance, is the inverse of the resistance in Siemens. Only one M, uppercase S. I is GV, equivalent to this expression. This is only another expression of Ohm's law. The current is proportional to the voltage across the resistor. We expect that when two guys like these two, a big one on the left and a little one on the right, when they're carrying a common weight, the big one takes most of the load and the little one takes less of the load. They split the load according to their capabilities. Now, let's review what is a voltage divider. A voltage applied to a pair of resistors in series like these two, it gets divided between the two resistors. That voltage, VAB, applied to the totem of two resistors, gets split between R1 and R2. The question is, how much of that voltage gets each one of the resistors? R1 gets V1 and R2 gets V2. The current I flowing through the branch will produce a voltage drop V1 in the resistor R1, given by Ohm's law. V1 is R1 times the current. But the same current has to flow through the resistor R2, producing a voltage drop, V2, also given by Ohm's law. V2 is R2 times the same current I. Now, the total voltage that we're splitting between R1 and R2 is the sum of V1 plus V2. If we substitute the first two equations in the third one, we obtain that the total voltage, VAB, is given by that expression: total resistance times the current in the branch. Now, we want to know what percentage of the total voltage VAB is V1. Well, you say it's easy. Divide the first expression, V1 is equal to R1 times I, by the expression for VAB. Divide them. So you can cancel out the current and get that V1 is the same percent of the total voltage VAB that R1 is of the total resistance R1 plus R2. Same percent. V1 is the same percent of the total voltage that R1 is of the total resistance. So if R1 is, let's say, 25% of the total resistance, then its voltage V1 is going to be 25% of the total voltage VAB. The resistor, I repeat, R1 gets the same percentage of the total voltage VAB that itself is of the total resistance of the branch. If R1 is 1/3 of the total resistance, it gets only 1/3 of the total voltage. Again, the resistor R1's voltage is proportional to the total voltage that is being split. Of course, that makes sense. the more to split, the more each one of them is going to get, and it's proportional also to its own resistance. Now be very careful when you're trying to use a voltage divider to feed current to an equipment. Let me illustrate that with a numerical exercise. Here we have a voltage divider, 20 volts divided between two resistors of 5 ohms each. Because each one of them is 50% of the total resistance, of course, the voltage of the middle point is only 10 volts. That voltage VA is given by the voltage divider formula and is, of course, 10 volts. And we are tempted to bring in some device, some equipment that operates at 10 volts and plug it into that voltage divider, hoping that the voltage is going to be 10 volts and the device will operate satisfactorily. But no, because the new device happens to have an equivalent resistance of 5 ohms. When we connect that in parallel with the bottom of the voltage divider, what we have there is an equivalent resistance of 2.5 ohms. Remember, 5 times 5 divided by 5 plus 5, 2.5 ohms. That means that the voltage divider now is going to give you a much lesser voltage. Why? Because 2.5 is only 1/3 of the total resistance of that new voltage divider. What is the total resistance of the new voltage divider? 5 plus 2.5, that is 7.5. Of course, the voltage VA is going to be only 1/3 of the total voltage 20, which is 6.66667 volts. Be careful. As soon as you connect a load that drains current out of the voltage divider, the voltage will not be what it used to be. As a homework, I suggest that you repeat this exercise with a new load that has 100 kilo ohms instead of 5 ohms. You've done it? Let's do that on the screen as well. We take the same voltage divider, and VA, of course, is 10 volts. And we plug in the device that has an equivalent resistance of 100 kilo ohms, 100,000 ohms. What is the equivalent resistance of the parallel of 5 with 100K? Do the math. That is 4.9998 ohms. It's almost 5. And when you do the voltage divider of 20 volts between 5 ohms and 4.9998 ohms, what you get is 9.9997 volts, which is approximately 10 volts. So for very large equivalent resistance devices, the voltage divider continues to operate very neatly. What is the current in the new device? I of the load, 10 volts divided by 100 kilo ohms, that is 0.1 milliamps. While the current in the voltage divider 5 ohm resistor is 10 volts divided by 5, that is 2 ohms. Check it out. The current that the load is draining of the voltage divider is 20,000 times smaller than the current in the voltage divider. No kidding. The voltage divider is practically unloaded. Another exercise. This time the load that we want to connect to the voltage divider is specified, not in ohms, but by the current that it will drain, 1 ampere. Check out, same voltage divider, connect the 1 amp load, and you say, well, wait a second, what is the voltage now Vx? I don't know what's going to be. Well, but you know that the voltage in the top 5 ohm resistor is going to be 20 volts minus Vx? Yes, it's going to be this, 20 volts minus Vx. Now, tell me one thing. This current here in blue, that current is Vx over 5. Yes, absolutely, that is a current in the bottom resistor of the voltage divider. Vx, unknown voltage, divided by the resistance 5 ohms. Why? Ohm's law, that is that current. And the current in the top resistor of the voltage divider, a voltage divided by resistance 20 minus Vx divided by 5. We can apply KCL to that node in the middle, can we not? Currents arriving in the node, 20 minus Vx over 5. Currents leaving the node, Vx over 5 plus 1 amp. There's your KCL equation. Solve for Vx, and you get that the voltage Vx is 7.5 volts. Neat. It is not 10 volts anymore. No, it isn't. It's less than that. By the way, what is the resistance, the equivalent resistance of the device you connected? Rx? Ohm's law. Voltage Vx divided by the current, 1 amp, that is the resistance of Rx of the device that you connected, 7.5 ohms. Enough of that. Let's work now with the mirror of the voltage divider, current divider. In this case, the same way that you can divide a voltage between two resistors in series, you can divide a current between two resistors in parallel. And the question is, what percent of the total current will flow through R1? R1 who? This R1. That current I1 is a percent of the total current I. Yes. What percent is that current I1 of I? Let's see. That is a current divider. We begin with a current divider and the total current connected between nodes A and B. The voltage between A and B is VAB, and it's the same in both resistors R1 and R2. The current in the first resistor R1 is given by Ohm's law. What is that? VAB divided by R1. But the current in the second resistor, I2, is also given by Ohm's law. VAB, the same voltage, divided by R2. You can apply KCL to this little Gauss surface and say the total current is the sum of I1 plus I2. Definitely. Substitute the expressions for I1 and I2 and look what you get. Factor out VAB. And now we have an expression of the total current as a function of VAB. But what we were looking for is what percent of the total current is I1. How am I going to do that? Divide this equation at the top for I1 by the equation at the bottom for I. Divide them, and this is what you get. VAB cancels out. Simplify a little, and this is what we get. I1 is the same percent of the total current that R2, the resistance in the other branch, is of the total resistance R1 plus R2. You say, what? The current in the resistor 1 is proportional to the resistance in the branch 2? Yes. Let's say that again. The current in R1 is the same percent of the total current I that the resistance in the other branch, R2, is of the sum of the two resistors, R1 plus R2. Let me give you a real-life analogy to bring this home, at least to allow us to memorize this expression. Imagine you're driving along a road and you find yourself a bifurcation of the road, and you know that you can get to your destination taking either of the two roads, the one on the left or the one on the right. However, the more potholes in the road on the left, the more cars are going to be taking the road on the right, correct? In electrical terms, if those are wires, the higher the resistance of that path, the more coulombs of charge that will be choosing this other path. Or, what is the same, the bigger the current in this other path, the higher the resistance of the path on the left, the bigger the current in the path on the right. In formulas, the one we got. The bigger the resistance R2, the bigger the current I1. And that is all, my invisible friends. I hope you have enjoyed this video as much as I've enjoyed putting it together. Thank you very much, and I hope to meet you again in our next video.